Hi, Matthew. Nothing happened in the last 2 minutes. You're just rescheduling the next lesson, which you won't be here also. Okay, target today is we need to finish up EMI, worksheets 1, question 14, together with worksheet 2. Anybody needs a hard copy of anything? What do you have? Okay. By the way, today will be our first exchange of grading papers, where you pass me your ACS butter and I pass you the third set, which is Dunman set. There are questions that are not in the syllabus that I think maybe your C cannot do one, just cross it out. Okay? So like for example, the first question of the MCQ, like the reading of the micrometer screw gauge one, that one is no longer in your syllabus. So no need to be able to read, no need to be able to find zero error. You just need to know how to use the digital micrometer screw gauge or the digital calipers. Okay, life is great for you all. Okay, last time we need to like screen our eyes and try to read the shapes. Okay, so later during the break, then we have our exchange of papers. Okay, if not, let's look into EMI worksheet 1. We have one more question. But I think the fact is the questions, I hope you are seeing them as getting more and more and more and more repetitive. Okay, because the answering technique, I keep saying the same thing, like change in magnetic flux. I keep saying Faraday's law. I keep saying Lenz's law. I keep saying like the induced magnetic field is such that it opposes it. If you keep putting phrases like this in, you are going to score well for EM. Okay, but today we are going to open another box called transformers, which the questions may look a little like like I thought I understood transformers last week. And then I tried the question, but I have to like whack my chest until I like go crazy. Okay, so later we will debug all of that. Let's start with question 14 first. To recap a little on what we need to do for EMI. When is it a case I need to use left or right hand? When do I use left hand, Charlie? When I have what and what, then I use left hand. I have current, I'm passing a current through. What else do I have? I'm putting two things in the middle. One north pole, one south pole. What is it? The magnetic field. So I have a permanent magnet. I put a current through, then I can decide how the wire is going to move. We even went to the extent of Newton's third law for that. In the question 7 that we flash on the screen and we try to spot, when the wire moves up or down, means the magnet will move the opposite way. That was Fleming's left-hand rule. Last week we talked about how you cannot just look at a question give me this means I use left hand. Question give me that means I use right hand. It must always be what did the question truly do? So if I really pass a current and I really have a magnetic field, sure, I use left hand. When I use right hand, I'll use. When I'm trying to find a current, do I have a current in the first place? Am I passing a current through the wire in the first place? No, I'm not. Okay, so what Charlene was saying was, oh, I pass a current through. That one I use left hand. The moment I don't have current, I'm not sending a current in. What am I trying to do? There's a wire. I'm trying to move it through the magnetic field. Or I move the magnet. Then I induce a current. Okay, so the moment I want to induce a current, can think of it as I'm trying to produce a current. I use right now. Then once you make this up, then you confirm like what you thought you do very well in exam. Then all actually come out opposite. Why? Because you use the wrong hand. Quite sad. Okay? But later I'll show you an instance in EMI worksheet 2, right? Where actually I use left hand to think about it. Okay, later we'll see the question, but let's go ahead, please. Okay, question 14. Question 14, I have this coil of wire wound on a piece of soft iron. Okay, then I purposely rotate a magnet in the gap in the soft iron. First question that you should ask yourself in exam is, should I use left or right hand? Okay, again, right, you cannot say, sure, this is EMI worksheet 1, therefore I use right hand. Cannot be like that. Okay, because exam really won't deliver for you anymore. How to think of this? Oh, I'm not passing any current through anything. I'm trying to induce a current. Therefore, I use right hand. Okay, let's look into how the FO mechanism works. Okay, maybe you don't even need right hand, but the idea is use EMF. Explain why the lamp glows when the magnet rotates. Okay, repetitive? Yes, repetitive. Faraday's law, right? Why the lamp glows when the magnet rotates? Simply put, think of the flow chart once again. Don't write down every single thing. Induce EMF, induce current because of changing magnetic flux. This is Faraday's law. Okay. When I always include these 4 points in, I will always be able to score. Good. I think your answer should have this, right? So no need to write down. I leave it alone. Is it more than this? Changing. I never write the Faraday person. Need to write Faraday's law. Yes. We need to quote him.
Induced EMF and induced.
Yes, induced EMF, induced currents. Absolutely correct. That was our whole thought process into it. Okay. Again, kudos to you all for finishing the worksheet. I know EMF worksheet took us 16 pages. Okay. Whether we finish or not, we shall see. Okay. But there are certain values and discussion points that we will discuss for sure. Okay, Abi, two alterations to make the lamp glow more brightly. Easy. Okay, now that we have gone through the idea again and again, right, I think this should be pretty easy. Either I use a stronger magnet, wound the wire, more turns, possible answers. Rotate the magnet faster, also possible as well. Extension to this question. This is describing or state two alterations or describe two alterations. What if it was an explanation? What is described and explained? Especially for this one, rotating the magnet faster. How will you explain your answer first? There's a larger rate of change of magnetic flux. Therefore, the induced EMF is larger. Questions? Good. Okay. Uh, yeah. Okay. One point I want to make here is this the same thinking that you should have for transformers? Recall what we discussed for transformers. We talk about when the voltage I step up, right? What happens to the current? Come down, right? Is this the same? When I say, oh, induced EMF is bigger, does this mean that my induced current drops as a result? Is it the case? You perhaps have some thoughts. Like you're probably in your head is like yes, no, yes, no, yes, I'm not sure. So the correct answer is no, it doesn't happen. Logic to this is you can think of it as if I use a higher voltage or higher EMF battery, does this mean I have higher current or smaller current? Higher current. If I link it back to V equals to Ri, vicious Ri, when I use a higher EMF battery, right? Okay, what happens if my resistance doesn't change? My length is still my length. My current that I'm going to send to the lens, that's why the I will actually increase. So don't confuse this concept. And so different, a bit different from transformers. Part C, soft iron core, quite standard answer. It is a way to concentrate your magnetic field lines. You concentrate magnetic field produced by the coil. You good? Soft iron core, always think of this direction. I'm trying to concentrate your magnetic field. Okay, let's go. Part D. Today the transformer question, right? There will be a quite interesting question of, should I use steel core? Right? For those who have tried, maybe you have encountered this question. You remember? Okay. Later I hear the answer. Okay, part D. U-shaped iron replaced by a piece of wood. Can does the lamp still glow? And the magnet rotates. Piece of wood, yeah, piece of wood. It actually does still glow. What's the logic to this? It is weaker because of the poor flux linkage. This one, phrase to pick up. If when I use a non-magnetic material made from wood, non-magnetic material, as the thing to try to concentrate the magnetic field lines, you can pick up this phrase called poor flux linkage, but there will still be changing magnetic flux. Still change magnetic flux, poorer flux linkage, therefore the induced EMF is weaker. That's why it will glow weakly, changing them. Yeah. Okay. So the conclusion to this, which you should wrap up your answer as well, is therefore the induced EMF drops. That's why it led to the lamp glowing more. Okay. Any answers you need to check for yours? That's quite important. Here is right. Even without that thing, right, that the magnetic flux can still be like vector towards there. So if you use a piece of wood, it can still like grab there, but then it's much stronger. When I have worked with lesson, so actually we have to understand that it is not actually trying to conduct potential changes, but rather trying to make them be my strong. So once it goes to one, the parts, the change and the pieces, so that's the method. Usually, the different actions similarly video to each other. So what's your idea? It's not I think previously fair, I think not actually. Oh, sorry. Is there a question? Just for the chat. Console. Still to me. So is it a magnetic field of the Earth? Karen, no. It is not the magnetic field of the Earth. It is still the changing magnetic flux of the magnet itself. Right. So if this is a non-magnetic material, it can still have like the magnetic field lines passing through it and passing through it, which causes an induced EMF in the coil. So not the Earth. If the Earth is a giant magnet, correct? The Earth doesn't like cause everything to be like attracted to one another. Thing like that. Okay, no problem. Let's go. Part E. Pretty quick, I think. Coil of wire now. I'll go on to the different parts. On the parts also, just a little. Okay. Okay. So the wire is now coiled around the soft iron core. Magnet again made to rotate, south pole moving out of the plane. Okay, this one. Okay. So now the south pole is moving away from this point A. Why is the question a little different in this case? Because I'm coiling the wire here. Therefore, I am actually trying to produce or induce rather an EMF at this position, at this position. Get the idea? So I coil around there, right? Means that there will be an induced magnet here based on the direction of the flow of current. Okay, so definitely I will have some induced magnetism here because of the induced current. Okay, how do you think it will change? When I rotate my south pole away, what happens? Toxic ex-girlfriend, right? If south pole want to run away, I try to induce a north pole here. South pole at the top. Questions? Okay, so at A, I'm going to have a north pole. The focus is really on here, this north pole. When south pole rotates away, the north pole will then approach it. What happens when the north pole tries to go near to A? Repel the invasion. So what will be the induced pole? Still north pole. Okay, so one rotation, it will still be induced north pole. First part. South pole moves away from part A. I induce north polarity. North pole approach remains north pole. Or not. Second one, I think you can guess what happens. Now the North Pole is trying to move. What happens? Toxic ex-girlfriend, I want to induce a South Pole. The second situation is like this already. The magnet has rotated until this way. Magnet rotated this way. I want to rotate the North Pole away. I induce a South Pole at A so that I can try to attract the North Pole back. When the South Pole moves towards A, I want to repel the invasion. Therefore, it will be still an induced South Pole. Okay, so second part, green color. North Pole moves away, acquires South polarity. All the way until the South Pole reaches part A again. Questions? Yes.
It moves away, it moves out.
South Pole moves out of the range.
But this is the, for example, as pole is moving up, plane of the people.
Moves out of the plane of the paper partly requires non-polarity. Can and yeah, can. But then how do you write about the North Pole approaching, North Pole moving into the paper? Sorry?
You
When North Pole nears part A, is it? Okay, can. Approaches part A, moves near part A. Okay. Olivia, which law is this? Lenz's law. Next. Okay. Yes, question. We need to describe about changing the solid poles in this. Oh, Juby, good point. That one will be a question where it will be described and explained. Here we are trying to describe how it changes. That's why this description about the changing magnetic flux is actually more of an explanation. Okay, I can bring you back to the question here. But part A, why do we bother writing about this? Because it's explaining induced EMF, changing magnetic flux. All these are explanations. Okay, I'm good with this. I think the MCQ is will be quite easy for EMI worksheet 2. I think the structure is a bit more difficult. Okay, let's see how this. Let's go. Okay, EMI worksheet 2. Six. Good. Question 1. 8. Thank you. 2. 1, 2, 3. 8. 10. 9. A lot of discussion points. 5. Thank you, Karen. Charlie? Already there? Or everything correct? No. Already there? Okay. Okay. We are nearing the end of the topical worksheets. Okay, I don't know how you all feel about your MCQ scores every time. Okay, honestly, I feel 7 out of 10 is a good score to achieve. If you don't manage to, make sure that after we discuss finish, you go home. If you can squeeze in some time here and there, review the questions. If you retain that knowledge, I hope the earlier topics, like for example, lenses. I don't know how much you have retained out of that. So when you are studying for the mid exam or anything, the question breakdown is important. Okay, so remember to revisit the questions. Okay, let's go. 4, 6, 7, only. Okay, let's go. Question 1. Question 1, or if you can actually draw in the axis, then you will be able to solve. Okay, questions don't require, it's not required to give you the axis. Okay, but what you can see from here is definitely a waveform. Right. So the waveform here, A CRO, we have gone through before in waves also, that if the y-axis is the EMF or the voltage, x-axis is always time-based, unless the question changes. If not, CRO is going to be that. Okay, so this shape of thing, right, the time base is set at 2 milliseconds per division, meaning the smallest square, I put in orange for time, is 2 milliseconds. Okay. Can see where we are going with this, right? Can we see the amplitude already? Once we join the axis, it becomes very clear. The amplitude should not be the entire thing, but it should be from the equilibrium to the maximum or the minimum. Right? So the peak voltage should be forwards. Okay? If you're okay with this, maybe the time was the issue. If the time is set at 2 milliseconds per division, I want to calculate frequency. How to calculate frequency from time? F equals to 1 over t. What can I see from this is definitely my period. Here to here is 1 period. How long will this be? 2, 4, 6, 8 milliseconds. 8 milliseconds equals to 8 times 10 to the power of minus 3 seconds. How to calculate frequency? 1 over 8 times 10 to the power of negative 3. I should get 1 to 5. I do, right? To be planning confirm. Later come out it's wrong. Okay, correct. Questions? Who got this wrong? Question 1. You ask me question 1. What's your answer? Oh, okay, didn't know the exist. Okay, can. More exam skills related. Okay, the rest of it. Do you need to check your answer? Okay, I think calculation question a bit more straightforward. If you are able to do it this way, we have question 2. 1, 2, 3, 5. Okay, let's go. Question 2. Okay, pretty similar. If you didn't do question, if you didn't manage to do question 1, maybe question 2 you will have struggled with it as well. Okay, question 2, same thing gives you a waveform. If you can draw in the axis, it becomes a lot clearer as well. Okay, this one I don't really require to calculate the peak voltage or anything. Okay, but I can see the period 0.4. T equals to 0.4 seconds. Time-based setting of a CRO. Yeah, if I want to see per cm how long is it long. So if period is 0.4, I can see that from this point to this point is 0.4. Therefore, each small square will be divided by 4, 0.1 seconds per cm. Yeah, that B. Okay. This is RI question. Okay, so R people not as smart. Because my brother from R, that's why I can say this kind of shit. My brother is stupid. Okay, no, my brother is smart. Okay, question 3. Yeah, this one. Time base is turned off. One question to ask you and you will know already. Is this X or Y axis? Time base. X axis on. Right. So if I know that X axis is turned off, what does that mean? It won't be moving this way. If it doesn't move left to right, my CRO screen should look like this. There will still be up and down, but then it won't move left to right anymore because the time x-axis is like turned on. Okay, so the waveform basically looks like this. If there's no x, meaning that everything like that is squished together, that's why there's only one straight line. Okay, so I'm drawing one that has like super high frequency already. So if I turn off that x-axis, you can just like come to me. Okay, that's why one straight vertical line. Okay. Whether you raise this, whether you all see the answer, then you all don't know what's going on. Okay. So this one just note that it's x-axis and your vision. Let's go to question 5. Question 5. Okay, so question 4, okay. No one asked question 4. Confirm. Okay, question 4 to me was I thought that you would have trouble with it. Okay, let's go on. Question 5. AC generator, frequency of 50 hertz. Yeah, so frequency of 50 hertz, what does it tell you immediately? Or what can you deduce from this immediately? Next time you approach questions like this, Charlie, what will you do with this? What can I find? Hi, or capital L T, is it? Period, right? C equals to 1 over F. 1 over 50, what? 0.02. Okay. 0.02 seconds. 0.02 seconds, but I look at the graph, oh shit, milliseconds, 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 milliseconds. How can I convert this? Times 10 to the power of 3, I should get 20 milliseconds. Okay, so the period is 20 milliseconds. I look and try to find the correct graph. Keyword in the question is starting from the position shown in the diagram. Why is this a keyword? Because it's in the horizontal position. We talked last week about how the horizontal position, when you cut, it is the maximum change in magnetic flux. Therefore, it is the maximum voltage. Answer will therefore be either C or D. I shouldn't start from 0. Okay, so how do we go? Yeah, I just need to ensure that the period is 20 milliseconds, then good. Therefore, answer is C. 20 milliseconds. Yeah. Yay, let's go. 8, 9, 10. Okay, you can give out the question for a bit. Okay, I guess a bit low key concern. Okay, even though you all managed to get this correct. Okay, the coin the generator will take 20 times in 1 second. I just wanted to check what does this mean. Regine, what does this mean? 20 times in 1 second. Yeah, literally this, right? In 1 second. Yeah, what is this physics term? Frequency. Okay, can. Okay, so that's why this frequency is actually from hertz. Okay, so you can actually calculate the period from here. Right? Okay. Okay, can. Okay, then I trust that you all know this. Okay, let's go to question. Sorry, forget again. 8, 9, 10? 8, 9, 10. 8, 9, and 10. Question 8. Wow, this one. Okay, sorry, this one I need to open because I cannot block really. Here. Questions. Question 9. Question 8, sorry. Okay, 240 volts, 6 ohms. I have primary and secondary coil. Okay, when you approach questions like this, especially in the structured question, we will do this later. Uh, be very clear on which values belong to where. Okay, sometimes they won't label inside the transformer for you. Okay, so pretty much like our yellow river, blue river, those kind of thing that we did in electricity. Maybe you can adopt a similar approach if you keep taking the wrong numbers. Okay, so what I like to do later, you will see as well for the primary coil. I can put it in blue, and I can see things like this. Okay. This one I can put, for example, in green, the secondary coil, then I have this 6 ohms. Okay, because sometimes a lot of values like thrown at you. Okay, so maybe just to color code a bit so that you can read it a bit easier. Okay, then the turns, secondary will be 1, primary will be 20, 1 to 20. Okay, what you can see immediately from this is, I told you don't really need to use the formula because what you can see is 1 is to 20. This is step up or step down transformer. Step down transformer. Okay, so this one, 240, I divide by 20. Divide by 20, I can already get 12 volts in the secondary coil. Okay, this time maybe you are not careful enough. We did a similar question in class before where we are asking for the current in the primary coil. Okay, so maybe you mistook as the secondary coil. Nothing too crazy here anymore, I believe. With this 12 volts and the 6 ohms, what can you find? Power. Right? Power equals to V squared over R. 12 squared over 6. Okay, 144 divided by 6. 24. 24 watts is the power in the secondary coil. What can I say about the power in the primary coil? Assuming it is an ideal transformer, it is exactly the same, 24 watts. Power equals to VI. 24 equals to 240 current. Therefore, current equals to 0. Do we get the logic? Question A answer is here. Okay. Did you all calculate current in the secondary coil? That's why. Who asked me question A? It's Eugene, Oliver. Do you calculate current in the secondary coil?
Yeah.
You did it. Okay. Did you manage to get 12 volts? You did. Then use V equals to Ri. Okay. So that would be correct for current in the secondary coil. To be 40. Oh, okay, wait. So you calculated current in the secondary coil first, is it? Okay, okay. We go by Olivia's approach a little. I want to help you see why that approach cannot work. Okay, this 6 ohms with this 12 volts here, if you use V equals to Ri, sure, 12 equals to 6 times I, current equals to 2 amperes. Okay, what you probably did was, sure, 2 amperes, secondary to primary, I times 20, 40 amperes. Correct, that's what you did, right? Huh? Oh, you use the formula. Okay, yeah. So the formula was Ns over Np equals to Vs over Vp. Say again. Is. Oh, Ip over Is. This works. This works. This works. If I purposely never really like introduced this one. Okay, because if you truly understood the divide and times thing, you don't need to apply this. Okay, so this you probably did this 1 to 20 wrongly. Did you? This is actually 1 over 20. Did you do 20 over 1? You do 1 over 20, okay, then I can continue. 1 over 20 therefore equals to I primary over 2. This one will be 0.1. Cross multiplication, 2 equals to IP times 20. IP equals to 2 over 20. Confirm something mathematical went wrong somewhere. But this approach is okay. Okay. So to emphasize again, because I thought Oliver was doing this, if any of you did this times 20 from here to here, this is wrong. Okay? Because the number of turns is not directly proportional to the current. Okay? In fact, it's inversely proportional. Okay? So let's not venture it. Okay? But this orange color approach by Olivia is perfectly okay. Any more things to check? If you need to clarify your approach, please feel free. Yes. Inversely proportional current, yes. 2A divided by 20, sure. Can. You'll get 0.1 straight away. Deep. Track carefully. Deep. Okay, good spots. Question 9. Oh, number of parts. Okay, question 9. Many small identical parts connected to this ideal transformer. I think I can go back. Okay. Secondary to primary, again, if you can put them in some colors. Okay, so green color I use for primary coil this time, blue color I use for secondary coil. Okay, the box I am putting at the secondary coil as my output. 2 volts and 2 watts. I can already calculate some stuff, right? Because there's P and there's V. I probably can calculate resistance. I probably can calculate current. Okay, let's look on first. 240 volts, and I saw that the turns ratio is 1:2. Turns ratio 1:2 means what? Secondary over primary. Secondary over primary means that I have a step down transformer. Step down transformer means I can divide by 2. That's why I divide by 2, I get 120 volts. Question is. Next, each bulb is 2 volts. How many bulbs can I connect to this? All bulbs, if connected in series, 2 volt, 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 I can do this 60 times. Answer A or B. Okay, so the number of bulbs can be calculated using the 120 volts divided by the 2 volts. So I get 60 bulbs. Primary current. How to calculate primary current? Can I find the currents that will be flowing through the secondary coil? What will be the current flowing through each bulb? The current flowing through each bulb from this 2 volt and 2 watts, right? What can I find? P equals to VI. Okay. So power equals to 2 times I. I can calculate current to be 1 ampere. Okay. Current in secondary coil, therefore, is going to be 1 ampere. If you manage to successfully calculate this, I think you will be fine. It's the last step to this. The power in primary equals to power in secondary. So pretty much the VI equals to VI. This side is primary, this side is secondary. Okay, so 240 times primary current equals to 120 Y. Primary current equals to 0.5 amperes. We good with this? Answer A. Right. Can I understand where you all are getting wrong at? Who didn't get the question? Do you understand the number of bulbs thing, is it? Okay. But do you manage to get the turns ratio? No. I thought it was the opposite way around. Okay, if I can point you to the part of the notes, right, that we talked about this, is here, the turns ratio, secondary over primary. So the turn ratio is found here. So is that one. See. Oh, right. Let's move back. Question 9. Question 10. Question 10 is a little more challenging, I feel. Keep 1,200 turns. Okay, but if you manage to see this, it becomes very easy. Let's see. 1,200 turns in the primary coil, then secondary in total 120. Immediately is this step down transformer. Step down. Right? Because I have fewer turns in the secondary coil. Fewer turns in secondary coil means that 1,200 is going to step down by how much? 1,200 to 120. Pretty much it's going to step down by divide by 10. Right? So in the secondary coil, I should expect 24. Okay. So this 24 volts is for the entire thing. This entire thing, I get 24 volts. Currently, I only want a pair of terminals for 12 volts. How? Potential divider concept can be sort of like thought about here. Okay, the easier way probably will be, how many turns do I need for 12 volts from 240 volts? 240 divided by 20, I can get 12 volts. 1,200 divided by 20, I get 60 turns. So I need a pair of terminals that has 60 turns. Which pair of terminals gives me that? QX 60 turns. That's why I can have the output voltage of 12 volts. Questions? Confused? Concerned? Concussed? If you okay. Questions along the way, just ask. We're going to pull on into the structured question. Other questions are quite interesting. Okay, let's go. Question 11. Ooh, EMI. In what, 8:14 already. Okay. Let's soldier on. 15 more minutes, then we have a short break. Okay? Question 11. Frequency 60 Hz, peak voltage 12 volts. Repetitive? Repetitive. CRO, what can I see? From the frequency, what can I find? T equals to 1 over F. 1 over 60, 0.017 seconds. Okay. Sketch the graph of the voltage produced for the two cycles. Let's start with the brown color line first. Let me highlight to be a bit clearer. The blue color highlight line should be your answer here. Okay, two things to take note of. Max EMF 12 volts given by the question. 12 volts peak voltage. Okay, so it should be a label of 12 and negative 12. Remember in AC generator, the direction of current reverses every half a cycle. Okay, that's why half a period later, I will be reversing direction. Okay, so 12 volts down to negative 12, back up to 12. Why did I start with 12 volts? Who started with 0? Common, right? Also good. Oh, everyone started with 12. Very nice. Okay, so the 12 must be labeled clearly to negative 12. Okay, then I will show two complete cycles. That's what they entered. Done. Anyone got a different period? Next, speed of rotation reduced. Okay, I didn't say divide by 2, but if you really go and halve it, it's fine. Okay, because it's still reduced. The reduced one will be in, let me put in like yellow color here, or rather just look at the red line. Okay, the red line here, what does it show? The EMF, the peak voltage has dropped. What else dropped? Because the speed is reduced. Two things. Number one, peak voltage drops. Number two, frequency drops. Frequency drop equals to period increase. Period increase or frequency drop can be thought of more simply as, oh, I need to stretch my wave up longer. Okay, that's why my period increased. Okay, no label needed because it just say reduced. Okay, unless the question is double, unless the question is half, triple, okay, then you need to be clear on the labels. Okay, questions. One cycle for part B. Seven. Okay, because they never state very, very clearly. Any more? Are you okay? Okay, let's go. Part C, explain the difference in the amplitude between the graphs. Okay, so this is the explanation question for Ruby. Just now you were saying the explanation. Okay, so this one, yeah, no Lenses law involved, rather Faraday's. Okay, so we should code that further as well. Okay, lower speed, smaller induced EMF because rate of change of magnetic flux is lower, is smaller, is slower. Can accept. Okay, so based on Faraday's law. Based on Faraday's law. You can see that some questions are putting, some questions are not putting. Okay. If you keep questioning yourself, hey, should I put or not? Then I tell you put. Okay. Because most marking schemes, or rather, I feel it's a bit hard. Okay, but let's be consistent. Okay, code the further. That's question 11, pretty fast. Question 12. Question 12 is really interesting. Okay, let's go. Question 12. Attempt to generate EMF across a copper rod by swinging between the poles of a magnet. It immediately, right, with this attempt to generate an EMF, this should be automatic clue to you, right? Attempt to generate EMF. Automatic clue to you that, oh, I'm going with EMI approach. Okay, EMI meaning it is probably a generator. Hence, I need to be using Fleming's right hand rule. Okay. So if you need a very clear direction, okay, these are things that you need to pick up. Okay, copper rod, sure, it is a conductor, not a magnetic material. Doesn't need to be. Okay, swinging between the poles of the magnet that I showed you. Copper rod in figure 12.1 is placed to position X, then allowed to oscillate, swing and swing and swing and swing. EMF induced across the rod. Not surprising, right? What's the logic behind this? There's a constant change in magnetic flux. Okay, let's take a look. Okay, direction we don't say first, but let's go on. Explain why EMF induced across the rod. Same thing. Swinging from X to Y, what happens? There is a change in magnetic flux of the magnet. Faraday's law induced EMF, induced current. Okay, or you can start at induced EMF. First question just ask why is there induced? Remember that magnetic flux already brings in the idea of thing. That's why the magnetic flux of the magnet is sufficient. Okay, let's go. Explanation question. B. Swing from X to Y indicate the direction of the induced current if switch S is closed. Switch S is closed. Okay. So what happens? It is oscillating from where again? X to Y. What's the direction of the force? Swinging this way, X to Y, going right. Right hand rule or left hand rule? Right hand rule. We established induced EMF. Force pointing to the right is turning for Karen and Juby. Force pointing to the right is magnetic field pointing up. Like this. Okay. Therefore, current is flowing into the page. Induced EMF is flowing into the page. Okay, therefore the arrow drawn this way into the page for the questions. C. Lenz's law. What is the direction of the EMF in the direction you indicated in D? Okay. Direction of induced current produces a magnetic field interacting with the magnetic field from the magnet to oppose the movement of the rod from X to Y. Okay. The blue color one is the one that we have discussed so far. Okay. This blue color one will be accepted as well. Give the standard phrasing answer that we go with. Direction of the induced current is such that the magnetic field produced will oppose the magnetic field that produces it. Phrasing check. Now we all write down, let me keep quoting. This will be possible this because if you didn't mention you also the closing and guarantee, but I don't know if the induced current is consuming. And what is the change in this? So it should be the magnetic field vectors. But all actions easier. Okay, sure. So with the printing papers that you are completing, Okay, when y'all don't complete this, can I be angry or not? Okay, but when you review back the questions, then make sure you can do it. Okay, so like cover the answers, make sure you can explain again, make sure you catch the key phrases, all this. Ooh, this one very interesting. Let me back finish first. Okay, next CRO. I'm connecting a CRO to see the output voltage. Okay, the maximum output they told us is 12 millivolts. Time base 15 milliseconds per division. Y gain 5 millivolts per division. Okay, the per division is simply referring to like your graph paper, the small square. Okay, so the 5 millivolts here, the one division is shown to you. So it's 5 millivolts for that one, or rather a big square this time. Okay. So what you need to be very sure about is your y-axis needs to be in millivolts, your x-axis in milliseconds, because that's what the question is giving you. Okay, so the 12 millivolts, I think, is pretty clear cut. I should be able to do peak voltage to be 12 volts until this point. Okay, if we draw a dotted line across this entire thing, 5, 6, 7, 8, sorry, not this, but the second one. Okay, yeah, keep peak voltage a bit off here. Don't take the answer as it is. This dotted line here should be the 12 millivolts. The peak should be all the way until this blue dotted line here. Yeah, then this one should be all the way until this line here. Okay, so the curve a little bit too short. Should be peaking at here. Peaking at here, all the way to here. Okay, how did I manage to find the period? Green color is your biggest clue here. If the 15 milliseconds per division, why did I intentionally make it yellow and green color? The 4 complete swings every second is a hint to me that I was asking Regine. Okay. So, Karen, let's check with you for this. 4 complete swings every second. You can just type up if you're feeling like throat cannot. Okay, 4 complete swings every second. What does this tell you? The rest, trying to draw the graph. Right? Frequency. Yeah. So frequency equals to 4 hertz. Okay, Karen. So I can find period. 0.25 seconds. When I put in milliseconds, 250 milliseconds. That's why the green color portion, we are putting 250. The green highlighted stuff on the graph. Okay, so every cycle should end at 250. For those who tried this, why is it the case that we are starting from zero? Ruby, why are we starting from zero? Why don't I start with 12 volts?
Because like in that position that it is in like the figure, there's like no EMF.
Okay, correct. At that position itself, there was no change in magnetic flux, right? So you should start from zero. Nice, thank you. Questions? If you are done with part D already and you haven't tried part E, try to think about part E. You agree with me? Okay, let's think about that. Student closing the switch, setting the copper rod to oscillate, drawing a possible waveform of the CRO to see what happens in T. Okay, I think I accidentally revealed the answer. For those who haven't managed to see the answer, let's think and discuss it. Yeah. Sorry, I still drawing. Your draw finishes about 30 more seconds to wrap up. Seems done. Okay, I.e. then, in closing the switch and setting the copper rod to oscillate, what do you think will happen to the output voltage or maybe even the period? Stay the same? Different? Increase? Decrease? Is it you all see like last question like that? Discussion. Okay, this is really up for discussion. Okay. And this question is pretty interesting. Is setting the copper rod to oscillate? Sure. Like normal is supposed to oscillate normally. Okay, but now I close the switch. What happens when I close the switch? I complete the circuit. Current can consistently flow through the copper rod. What happens? When there's a consistent current flowing through the copper rod, what will there be around the copper rod? Magnetic field. Right? Current carrying wire always got magnetic field around it. When it interacts with this north and south pole, what happens? Or rather, the direction of the current, right? It's force, yes, true. Right, current. So the force that is going to be produced is going to oppose the magnetic field that produced it. Get the idea? So how do you think the copper rod will start to oscillate itself? If it's trying to oppose the magnetic field changing it, will it start to go faster or like go slow? If it's trying to oppose, you will always try to slow down. Right? I don't know whether you all seen this video in school, but I think Zhi asked me about this copper, the magnet falling through a copper rod experiment thing. Have you ever seen it? Let's try to find it. Copper rod falling through, magnet falling through copper. Magnet falling. Dropping a magnet through a copper pipe. Okay, let's see. Share some.
Hold on, am I running? Okay, we're going. Yeah. Do that again.
Do that again.
That is.
Okay, do you see it? But it's like kind of slower,
Okay,
right?
we're going. Yeah.
Like lag, like a computer lag. So the magnet fell like slower inside. The whole idea behind it is actually lenses. Why does it occur? Because the magnetic field that is produced around the magnet, or rather in this case, the copper tube is going to oppose the magnet. Okay, so the magnet is going to fall slowly through it. Okay, the idea to this is pretty similar. Okay, so the copper rod is going to have a magnetic field around it so that it opposes the magnetic field that was producing the EMF in the first place. Therefore, the copper rod is going to start to swing slower inside the when it oscillates. Okay, so when it swings slower, what happens to the EMF? Smaller. Okay. Does anything happen to the period? When it swings slower? Yes. Right? Direction, rotation gets faster. We see the frequency gets very large, period gets very small. Okay, the marking scheme here honestly didn't mark on the period, but what I want you to know will be the period, will be the pattern. Okay, so the answer to this is really amplitude smaller, period longer. Okay, and let's try to sketch this in. If the answer is not directly given, let's try to sketch in blue color, pink color. Okay, I try to draw in pink color. Okay, amplitude definitely gets smaller, and period getting longer means frequency gets smaller, meaning I stretch my wave out longer. Okay, so since it doesn't say by how much, I don't even need to be super precise about this. Something like this will be good. Make sure your bottom and top is the same. Negative demonstration. Let's go with 10. 150, 300, 450, 600. Okay, okay, let me try to do it properly. If I draw in my points first, okay, if you struggle to draw like me, if you plot in the points first, you will see it becoming easier. 450 at the top. Four fifty cutting blue and 600 in the sorry, let me read that. Okay, so something like this. Amplitude getting smaller and the wave getting stretched out more. 450, 600. Yeah. Okay, so something like this will be marked correct. Okay, so smaller amplitude, longer period. Just okay, let's have a break. This is question 12. I start the break after you're actually done. If not the break finish already, then I'll like just finish the question. Okay. Break will start in 20 seconds. Yeah, I hope you can help yourself to some snacks if you want to. Hey, sorry guys, very long time buy bubble tea. Cause we are having pizza. Okay, after the pizza during the New Year, then the bubble tea come back. Very simple. Okay, good chance for you, yeah, to pass me your ACS buffer paper. We are done with it. And for me to exchange you in return. Karen, can you remind me when you see me to pass you the next set of relief paper? Will I see you on Wednesday? I need to see you on Wednesday. Or you recover by then. Okay, thank you, Karen. Okay, you guys know. Anyways, how was the paper? Yeah, so then you managed to spend a lot of this up. We have division ratings up. And what's the next thing is well. Good one. Things we have done. Oh, you asked me also. Fine. The tank is still in Singapore. Tank is still in Singapore. Right. So she's saying that okay. But she's taking pure. This is interesting. Okay. Let's move on. Question 13. By 9 p.m. I need to start with radioactivity. Okay, so let's see how much we can cover. Okay, but I don't want to skim through things, but also because the transformer one, I don't know. I think question 13 is still manageable. Some questions may get a little bit confusing. Okay, I think this one not too crazy. The step up and step down transformer, we have talked about the concept and why we need to use it. Okay, so the reading here basically is already knowledge that we know. Okay, nothing much to break down here. Okay, but in long readings like this, when you encounter database question or anything, pick up the values. Pick up the values and in transformer questions, right? Why are they in different colors? Because I know the power station one, the 25,000, 12,000 amperes, right, is going to be at the primary coil. Because the power plant can only come out of the primary coil. Then I either step out, step down. In this case, I want to step it up after it comes out of the power plant. Okay, so the secondary coil therefore will be 400 volts there. Okay. Transmitted across country through long cables. Yeah. Okay, so what's the whole idea behind this? You all recall the idea? Why do I want a very large voltage? I mean, what's a large voltage for? Why do I bother doing this? I guide you a bit. I'm using the formula P equals to VI first. When I have very large voltage, what happens to current? Decrease. Right? P equals to VI with large voltage, current drops. That's the whole idea, right? Current drops for what? What's power loss? V square over R. Don't use that because the V can get complicated. Should adopt for I square R. I square R. Okay, the V square over R, if you think about it, right, then the V set up a lot, right? Then my V square over R will be large. Correct. So the V square over R can be a bit risky when you think about it for power loss. Okay, so power loss, if you stick to I square R, you will be generally safe. Okay, so I square R, that's why the current comes down, the power loss. Okay, this was the idea that we ended off with last week. So that's the purpose of transformer. Okay. Can I just confirm that Judy is back? Are you back? Okay, that's quite see my screen, I don't know. Okay, for 400,000 volts, therefore, it's definitely going to be a step transformer. 25,000 to 400,000, I can easily find the turns ratio. Okay, the turns ratio, therefore, is going to be secondary over primary. Should I expect the number to be more than 1 or less? If it's a step-up transformer, it should be bigger than 1. Secondary coil must have more coils. Okay, so the turns ratio therefore should be 16 in the simplest form. Okay, so 400,000, 25,000. Nothing too much. This makes it a bit clearer. Just going to write in first. Let's move to the next one. Output current from the transformer. Meaning at the secondary coil, how much current is going to come out. Okay, nothing too crazy here. Okay, but but if you use the Vs over Vp equals to Ip over Is, I am a bit scared that you will like terbalik around. Okay, so if you stick to this, then you manipulate, I feel it's safer. Okay, so I recommend you use the blue color words, thinking about, power at the primary equals to power at the secondary. Okay, because we are assuming an ideal transformer. Okay, therefore answer is still Is equals to 750 amperes. You good? Okay, not too difficult. Part C, advantage of transmitting through at a high voltage, exactly what we have discussed already. Okay, voltage high, current flowing through is low. Current flowing through is low. There will be smaller energy dissipated to the surroundings, smaller amount of energy transferred to the internal store of the surroundings. Okay, so the energy loss as thermal energy, let's change the phrasing from this paper. This will reduce the energy transferred to internal store of the surroundings. And the blue color one is for reference. Throw it into the answer if you want to. Personally, I throw in. So P equals to VI, make it very clear. P equals to I square R, after that power loss, make it very clear. That's question 13. Question 14. Really? Question 14. Part A. Transformer only works when it's connected to AC power supply. This time we talked briefly about it. We didn't really write down itself. Okay, but we should already understand the idea. What's the general idea behind this? Changing magnetic flux. Right? Again, I told you, the transformer is not a case where it is directly passing the current to the secondary coil. If that defeats the purpose of a transformer. So the transformer has to be a changing magnetic flux. So what happens is, number one, AC, there will be a change in magnetic flux. Therefore, EMF can be induced at a secondary coil. Okay, first part, EMF induced because there's a change in magnetic flux. In a DC supply, however, there is no changing magnetic flux. Thus, using Faraday's law, there will not be an induced current. Okay, so understand the thoughts behind this. Okay, so let's be a bit more careful in the studying here. Okay, so the secondary coil, or rather, when AC is involved, AC is involved, I have constant change in magnetic flux, induced EMF, Faraday's law. DC, same thing. Still Faraday's law, but there is no change in magnetic flux. No induced EMF, Faraday's law. If Faraday's law, honestly, if you write one time, it's fine. If you want to quote both times, because you are explaining that thing once again, please go ahead. Give 2 marks. 14B. Okay. Can I finish this first? Okay, part B. Still not suitable for the core of a transformer. Whenever you compare steel versus iron, what's the difference? We always talk about hard versus soft. Okay, so that should be the first instinct, first answer you should throw in. Okay, hard versus soft. Yes. Why do we put more? Secondary coil in sorry, why do we include more EMF in secondary coil in more EMF? Oh, this one is it? The more EMF? More EMF induced in the secondary coil. Here the answer key is trying to make more of a comparison between DC supply and AC supply. Okay, technically, for DC supply, there will still be a little bit that is momentary. That's why the more induced EMF can still apply here. Okay, so the DC actually causes a temporary change in magnetic flux. Okay, so there's no like induced EMF that is like constant. Okay, 14B. Still hard magnetic material, difficult to magnetize, demagnetize, as required by the core of the transformer. If magnetic flux density, pick this up as well. In a hard magnetic material like steel, magnetic flux density is weaker. Can think of this as how much it concentrates the magnetic field lines. Okay, magnetic flux density weaker for hard magnetic material. Okay. So only two parts to this. Okay, hard magnetic material, difficult to magnetize, demagnetize, magnetic flux density weaker. Let's go. Let's see. Okay, just for knowledge, for actual transformer that are used, there's actually a little bit of steel inside. Okay, so if you like go and find a real life example of a transformer, it's not like pure iron inside. And it has to be doing with like other reasons than this. Okay, I'm not actually sure of that. Okay, for part C, electrical power, why I put it in green once again? Because I want to see primary, secondary very clearly. Okay, part C, electrical power generated at power plant was what came out in the first place. 5.20 megawatts. Immediately, mega, giga, whatever coming with the prefix, I try to change it to SI units. Then I don't need to be like, oh shit, I keep forgetting. Okay, put down here 9.2 times 10 to the power of 6 watts. So that I'm ready to use it. Okay, in fact, I should also write, 11 kilovolts. Remind myself, 11,000 volts. Okay, then I will make the silly mistake of units. Okay, that's one of the last mistakes that you should make. Okay, because we know already. 220 kN. This one I didn't convert because later I saw 0.45 ohms per kN. Okay, so this is fine. Okay, so the green color one is your power. I have 11 kilovolts at the primary coil. Secondary coil, I want to find out. Okay, let's see. Okay, this one a bit more challenging because the transmission cable have resistance. When they have resistance, 0.45 ohms per kN. When I go over 220 kN, you can imagine that it will be a relatively large resistance. Okay, let's take a look at C part 1. Current generated at the power plant. I have power, I have voltage. Can I calculate current? Pretty easy this one. P equals to VI. Current therefore equals to 473 amperes. Okay, resistance of the transmission cables also very straightforward. Now that we talk about it, 0.45 ohms per kN. For 220 kN, it's going to be 99. Easy? Let's go. Sign to you again. Minimum ratio, this one is simple. The minimum ratio of the number of turns in a secondary coil, or this one, right? Ratio of the, yeah, this entire bracket here can be simply summarized as turns ratio. So to make the question a little bit more digestible, determine the minimum turns ratio so that transformer P energy loss is below 10%. Whenever you see questions like that, don't panic. Go to the value first. Oh, question wants me to find below 10%. Whatever you do, right, you will need to calculate using 10%. Okay? So the 10% is supposed to help you. Initially, the power of the primary coil was given in the question, 5.2 times 10 to the power 6. Okay, so I want this to be less than 10% power loss. Energy loss is less than 10%. Therefore, the maximum power loss that I should have is 10% of this, 520,000 watts. Okay, so again, this one is from 10% of the total power, 5.2 times 10 to the power 6. Okay, so this is the maximum that I can use. Okay, let's go on. Okay, the maximum power loss therefore will be this, and what next up will be power loss in transmission cable that I can find. I need to ensure that this is going to be below 520,000. Power loss can be calculated using I square R. So I want to try to determine the current. Why so? I go back to the diagram a while first before you write down like the numbers that might not make any sense to you. Okay. What am I trying to do here is step up. My transformer step up and I want a V1 to be large so that current is low. So that P equals to I square R is maximum value 520,000. Less than 520,000 watts. Okay, appreciate this first before we jump into the values themselves. Okay, if not, the values might not make any sense to you. So what am I trying to do? I'm trying to make sure that I have a turns ratio that is large enough so that this V1 is making the current very small. Okay, see where we're going with this. Next part, therefore, will be I want to find out the I square R equals to 520,000. How much current do I actually need? Okay, so the current minimally must be 72.47. Okay, or rather, sorry, maximum current that I should have, 72.474. Anything more than this, I will have too much power loss. Okay, so this one, when you drop it down, make sure you understand the idea. This one is actually the max current I can have. Why am I going by the current approach? Because power loss must be calculated with I square. From this current, then I can work one step back to try to find out the voltage. With this current, how much voltage do I need in this current to come through? From P equals to VI. Okay. First part, got it. So current must not exceed 72.4. Therefore, my voltage must be above a certain amount from P equals to VI. If we break this down together, ignore the blue boxes. Ignore the blue boxes. If follow along, 72.4 amperes is what I want. How can I derive this, right? I look to the question. Ideal. Where's the ideal? Here. If the transformers are ideal, meaning the power 5.2 times 10 to the power 6 is going to be the power at the secondary coil. Does this make sense? So again, the power at the primary coil is going to be equal to the power at the secondary coil. Same. PP equals to PS. Therefore, I can actually find out the voltage that I am interested in. So the formula looks a bit too complicated, looks a bit disgusting. avoid that if you find that very confusing and disgusting as well. Okay, with the 11,000 volts that I have here, I want to make sure I can get a certain value. Okay, so with the power I have here, 5.2 times 10 to the power of 6, this is exactly what I want at the secondary side. Ignore the blue box for now. The power in my secondary coil, therefore equals to Vs times Is. You good with this? What will be the power in secondary coil? Again, will be your 5.2 times 10 to the power of 6. Voltage, current maximum should be 72.47. From this, you can calculate your Vs. Vs equals to 71823.2 volts. Hopefully, you won't get too overwhelmed with this. If you are good with this blue color box, it is not wrong. It is not wrong. I just want you to walk through with me with the thought process here. Okay. So with the Vs that I managed to calculate, I want to find out the turns ratio. I have the 11,000 in the primary coil. How many turns do I need in the secondary coil in order to achieve this? That's what the question is. Okay. Okay. So the primary voltage is here, 11,000 volts. Okay. So if I can lay this out a bit more like systematically, right? Primary, I have 11,000 volts. I want my secondary to be 71823.2 volts. Okay. So turns ratio. Okay. So the turns ratio will be your NS over NP. Okay. A bit no choice like this one, I guess. Okay. NS over NP is my turns ratio. Therefore, will be my 71823.2 divided by 11,000. I think some of you are comfortable with the current you flip around. Okay, but again, track carefully. Okay, I think Regine and Olivia, I think you all use this approach. Okay, so this is totally okay. Okay, this is actually a slightly longer way for us to get there. Okay, but to me, a much safer option because you need to think about the direct proportion only. Okay, so this should lead you to 6.6 as well. Okay. Question 15, which I'll leave it to next week. Seems like it will be the case for other courses as well. I'll update you on Woodlands. Okay. We are good with EMI worksheet 2. Okay, except for the last question. Okay. Thank you for trying. Sorry that I didn't manage to cover question 15. Okay, but I hope this transformer question cleared the doubt. Because this part 3 over here can be complicated. Okay, let's move into radioactivity. Yes. Okay. Okay, so we are on page 1A of curator notes. Yeah. Okay, radioactivity, to put it simply, if you are interested in killing people with atomic bombs, then this topic becomes a bit quite interesting. Quite interesting. Okay, have you all watched Oppenheimer? Anyone watch? I attempted to watch, okay, but I fully understand it. I didn't. I thought it was like, wow, some history god. I was going like, wow, I last time take pure history and World War II, all I know. Really, I'm going like actually don't understand. Okay, but honestly, the Oppenheimer show, I'm more interested next time. I think it's M18 actually. Yeah. So good that you all say no to this. Okay, so the Oppenheimer whole show to it was actually he is the father of atomic bomb. Okay, so if you learn pure history, either history also, the bombing of the Hiroshima and the Nagasaki, that US dropped on Japan, the making of the atomic bomb was actually in the show. Okay, so it's pretty crazy. Okay, and to think that now we are even like the atomic bomb now can be even more disruptive, not disruptive. It is very scary, scary. Okay, so radioactivity is actually about the idea. Okay, so later we'll see a snippet of the Oppenheimer show where he tested the atomic bomb. Okay, because like back in the days, like they totally have no clue. Now it's easy for Kim Jong Un to say, "Hey, I'm ready to like strike you" or anything like that. Some bullshit he's saying. I don't know whether it's real. I think it's real because they keep testing and shit. Okay, so it's pretty scary. Okay, but last time they need to do all those tests and everything. Okay, but let's move into radioactivity first. Okay, the first one I don't want to spend too long on these 2 pages simply because it's chemistry related. Okay, but low key, I want you to appreciate the atom just a little bit more with this like Rutherford guy. Okay, I don't know whether you all watch this Rutherford gold foil experiment before. Okay, but this guy was trying to like research an atom. Currently today we see this we are like, hey, easy chicken feet. Okay, but last time like I totally have no clue it looks like this one. So the Rutherford guy actually like did an experiment, then came out with this one, like, oh, an atom looks like this. Oh, okay, so the Rutherford guy actually did this. Okay, so this stuff, nothing too crazy, but in case your chemistry, some of you don't take with me, right? This one, the big number and small number thing, I need to be very clear. Okay, because in the periodic table, it's split term. Okay, so I just need to know that the big number is proton and neutron. The small number is proton or electron. Okay, but today, right, our focus is not too much about like see the periodic table or anything. Okay, because we are interested more in something called the nuclide notation. Okay, isotopes I won't spend too much into it as well. Okay, but isotopes definitely definition might be something that they might throw in. Okay, but I still feel might be more chemistry. If I understand the idea first, same number of protons, different number of neutrons, definitely. If that's isotope that we learn in chemistry section. Okay, but what happens in physics for radioactivity, the focus is nuclide. Okay, this nuclide is nothing like too scary or anything, okay, but you need to just switch your attention a bit to focus on the nucleus. Oh, we are focusing on the nucleus itself. Therefore, whatever you see here, the numbers, we are talking about the neutron number, proton number. We are not really interested in electrons. Okay, so that's basically what the nuclide notation can be thought of more simply. So what example we won't go through is very straightforward. Okay, but I want you to appreciate the terms just a little bit more. Let's take a look at what this Gufford guy did. Okay, I will fast forward the video. I don't need to watch the video. Erase it. My friend.
Later revisions of the atomic models.
Okay, sorry, a bit too fast. Okay, I slow down to 1.25. Okay.
The early atomic model was proposed by J.J. Thomson in 1897, following the discovery of the electron and its mass. Thomson hypothesized that the negatively charged electrons in an atom should be counterbalanced by positive charges to make the atom electrically neutral.
True, right? But it's electron inside the middle. It's not. So this previous guy said that electron outside.
Therefore, he suggested a plum pudding atomic model. He postulated that electrons are embedded in a lump of positively charged cloud, similar to raisins spread in plum pudding. While this model succeeded in explaining the atom's neutrality, it hatched other questions, such as how could two opposite charges coexist in an atom without being unstable? And since it is known that electron mass is so tiny, then what makes up the atomic mass? Ernest Rutherford, who was once a protege of Thomas at Cavendish Laboratory, sought to answer these questions through his gold foil experiment in 1909. Together with his co-workers Hans Geiger and Ernest Marsden, he conducted an experiment in which a sample of radium was stored in a plumber box with a very small hole, emitting positively charged alpha particles through it. The box was positioned in line with the thin gold foil that was surrounded by a zinc sulfide screen. While the alpha particles from the radium hit the gold foil, they scattered and produced light flashes that were detected by the screen. Based on the plum pudding model, Rutherford thought that most of the particles would pass through the foil, while some are slightly deflected due to their encounter with electrons. Initially, the experiment results were indeed consistent with his assumption. But what followed next was totally unexpected. Some particles encountered large angle deflections, and very few about 1 in every 20,000 were bounced backward. Rutherford thought there must be something positive, minuscule, yet heavy in the center of gold atoms that repels positive alpha particles and essentially makes up the atomic mass. He called it the atom's nucleus. The results strengthened the previous notion about the existence of positively charged particles, later known as protons, within atoms. And since the majority of the particles pass through, he suggested that an atom is mostly empty space. Rutherford proposed an atomic model named the nuclear model based on this inquiry. He stated that this is a tiny nucleus with positively charged particles inside, and it is surrounded by electrons.
Okay, that's about it. Okay, honestly, this one was test in exam. Okay, but I just wanted you to see the atom a little bit more. Okay, that the atom, the nucleus itself in the middle, okay, really doesn't consist of the electrons. Okay, so this is really just the background of how atoms really came about. Okay, I think the more interesting one is like the atomic bomb and shit, okay, which will be coming up soon. Okay, but honestly, the goal for experiment was like there was a word called alpha particles inside. Okay, which is something that will be related to what you will need to know. Okay, alpha particles later we will see inside the creator notes as well. It is actually positively charged. Okay, so the positively charged, that's why this guy did an experiment, right? It is supposed, most of it managed to go straight. If it goes straight, means that pretty much nothing happened to it. Okay, then he saw some of it gonna bounce back or deflected in different directions. Okay, but then basically he realized that there's no electrons inside the middle. Okay, so nothing too much here that we need to like be very concerned about. Okay, even if you didn't really understand the goal for experiment. Okay, it's really something for you to see how an atom is actually being constructed. Okay, so it didn't get out of thin air. Okay, we go to the main focus of reading. Okay, we talk about nuclear decay for a bit, then we shall go on to the treating and radiation. Okay, we talk about this for a bit first before I show you the Oppenheimer video. Okay, the nuclear decay, right? Also called radioactivity, is the whole idea of this radio. Okay, what happens is there are two things you need to realize that they are spontaneous and random. Okay, spontaneous random meaning, for example, like you throw something like a box of colored cubes that you just throw, then they are randomly scattered all around. Okay, so spontaneous means that there's no external influence. Random means that it is impossible to predict. Okay, so nuclear decay, you can think of it as, it's going to change in form while releasing certain things. The whole idea of like radioactive, very dangerous, all these things is because they are decaying. When they decay, then they like have some radioactive stuff that is coming out of them. That's the whole idea. And the radioactive stuff that we are saying is your alpha, beta, and gamma. Okay, so long idea short, right? The nuclear decay, you can think of it as, I am releasing either alpha, beta, or gamma. Okay, so something is happening to the nucleus simply because they are unstable. This stuff over here, they are unstable. Therefore, they decay. Yeah. Okay, this one, if you can help me link this to organic chemistry, right? If organic chemistry, we talk about cracking. Okay. For cracking, what happens? It's like chopping up a salmon fish, like chop, 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 chop. What do I need to make sure when I balance the equation? The number of atoms are always on the same on both sides. The idea here is similar. Imagine this decaying as like a salmon fish getting chopped. If a salmon fish chopped, salmon very expensive, I don't want to waste any task. Right. Okay, so what I want to ensure is the number of the number at the top, number at the bottom still remain the same. Okay, take a look at the first one, the alpha decay. This helium over here is your alpha particle. Alpha, you can write it like this, alpha particle. Okay, and it's super important to realize that this is not helium atom. Alpha particle is not helium atom because that's not our focus anymore. We shifted our focus to nuclide notation. So this is showing the nucleus of the helium. It is helium nucleus. Things to note, therefore the top number and the bottom number does not change. The 235, 231, 4, 92, 92. Go to beta decay, same. 235, 235, 0. 92, 93, minus 1. When I add up, it is still the same. Okay. Electron for beta particle, right? This is your beta particle. Electron for beta particle, we have a minus 1 at the bottom, meaning to say it has negative 1 protons. Okay, simply because electron is negatively charged. Yeah, okay, for the gamma decay, there's something that I need to help me change. Okay, if not, it wouldn't make sense of our 7 fish thing. Okay, so it truly must remain the same. So your 235 breaking down to 231 will not make sense. Okay, so if you really want to break this down, this should be 235. Okay. So the top number, bottom number shouldn't change. That's the main idea. The reason why I can change these numbers very easily because they exist as isotopes. Right? So the number of neutrons can always be adjusted. Makes sense. Okay, so this U stands for uranium. It is one of the most common radioactive substances. Okay. So why is it able to undergo this radioactivity? Simply because you can imagine that the nucleus is unstable. Okay. Once again, all these things that we are seeing here, they are all the nucleus. The nucleus of uranium, nucleus of uranium. Okay. Anything else? One more example for gamma decay. Gamma decay, you can also write this example. 238, uranium 92. For gamma, typically, gamma typically you will see an accompanying particle together. So you can break down to this thorium. Of course, I need to make sure everything is balanced together with gamma 00. Okay, so this might be a common equation that you're going to see as well. Nothing changed. The top number doesn't change, bottom doesn't change. In conclusion, the gamma is actually nothing. It doesn't have any mass, it doesn't have any protons. Okay, that's why in the table that you're going to see below, right? If alpha, beta, and gamma, we need to be very clear about their charge. Some of you may have encountered this question before already. Okay? The 2 plus, 1 minus, and no charge is going to determine. Okay, I don't cut the words. It's going to determine how they behave in a magnetic field. Because they have charge, right? They are going to behave differently in a magnetic field. In what sense? It is a positive charge. When I pass into a magnetic field, it functions like a current. If I pass beta particles in, beta particle is the same as electron. Beta and electron, same thing, exact same thing. When I pass beta particle through magnetic field, what will happen? There will be a deflection. How do I find the deflection? Fleming's left-hand rule. Okay, so beta particle is an electron, therefore you need to reverse the direction to see the current flow if you use Fleming's left-hand. Can you get the logic? Lastly, gamma ray therefore will not deflect. Because it has no charge, it will not deflect. I don't even bother doing Fleming's left-hand rule for gamma. Okay, let's link this a bit to EM waves. In EM waves, what did we learn about? gamma rays. Remember our song? Do you all cringe at that song still? The electromagnetic spectrum, right? All the way until gamma rays, it is the highest frequency. But gamma rays has super high frequency inside electromagnetic radiation. In the EM waves, gamma rays has the why not slow down? Highest frequency. Highest frequency. That's why we can call it an ionizing radiation. Highest frequency. That's why it's an ionizing radiation. Penetrating power, we'll talk about it on the next page. But general idea is there already. Anything else? Yeah, I'm good with this. Any questions to check? The nucleus over here is has been highlighted above, so be very clear about this. Okay, that it is not helium atom. Okay, and everything that's happening here, right? Okay, when they decay, you see something being given out. This is radioactivity. Okay, and this giving out of things, right, is in terms of energy, which can be used to, like, for example, produce electricity. For example, to bomb people. Okay, we take a look at the Oppenheimer video. It's not long. This Oppenheimer guy, oh, I was watching this one. Explosion scene. I'm not sure why they muted this part too. But basically they're inside the thing. And they're like carrying out experiments. Atomic bomb. Okay, okay, very underwhelming. Okay, but the general idea to this, right, is I knew to see what atomic bomb is. Atomic is from atom. Right, why do we learn about atoms in the first place? It is related to radioactivity. Right, so atomic bomb, right, is actually an idea of nuclear, later we'll see nuclear fusion or nuclear fission, more towards nuclear fission, where large amount of energy are being released. Okay, later we'll take a look at the idea, but let's move on first. Okay, so this is what the atomic bomb can do. Okay, penetrating power is a big part of the entire like new syllabus that they introduced into. Okay, that we have to be familiar with the penetrating power. In short, all the alpha, beta, and gamma being introduced, only gamma is very high in penetration. Okay? Gamma ray can penetrate deep. Beta, a bit. Alpha, even more deep. Okay? So alpha is the smallest, followed by beta, followed by gamma. Okay, so it can go deep into something thick, like the lead here. Okay, easily stopped. Penetrate slightly, penetrate. Okay, nothing much here already. Okay, so if as long as you understand this, right, questions can come in the form of which one will travel further if I put a maybe 10 cm block in between them. Okay, so as long as you know the penetrating power, then you'll be able to answer questions like this. Okay, anything else from here? Yeah, okay, all these equations that you can see here as well, the idea of the 7 fish chopping still holds. Top number same, bottom number same. Okay. Next key concept, background radiation. Okay, background radiation, yeah. Okay, background radiation, we can simply think of it as something that's occurring like in the background. Something like that, like apps that are running in your background in your phone. Okay, background radiation is radiation that's happening, meaning no radioactive source. Okay, so background radiation can be man-made, can be minerals. Recommend you to know a few examples so that it is so that you can write like in, you can do tests for this. Okay, X-ray machine is one of the man-made background radiation that can happen. Okay, basically, you can think of it as I don't have those kind of radioactive stuff. Then I purposely introduce them. These are my man-made elements. Okay, then the minerals one are more natural resources. These are like your crops. You can have fruits like banana, for example, also. Okay, banana is actually high in potassium. Okay, so the potassium of nucleus can undergo radioactivity as well. Okay, so I don't know whether you also like you shouldn't eat too much banana. If you go help check up before then they like test for your potassium level and everything. Because my uncle recently just went, then his potassium level like very high. Because he eat banana every day. Okay, so the doctor like advise, hey, don't eat too much banana. Because banana got this potassium thing inside. Okay, so this potassium is not really like the potassium that you see in the periodic table. Okay, it is not exactly that element, but rather it is a different form. Okay, with a different number of neutrons, so that the nucleus is easy to decay. Okay, so it's not exactly the same as the periodic table. Lastly, half-life. Okay, half-life, the idea of, I think it's not difficult to grasp, okay, but if you read questions wrongly, you will get into trouble. Okay, half-life, the idea is really just about decreasing to half the original value. Decay to half its original value. Okay, and I don't know whether you have this concern, okay, but when I see value, I honestly don't know what it is. How can question test you? Original value can come in the form of mass, the value can be mass, or number of particles. To be more specific, number of atoms. Okay, so what can happen is it can decay. For example, I have 100 grams, go down to 50 grams, 25 grams, etc., etc., etc. Okay, that's why you can summarize the idea using this formula here. Okay, which honestly, do you need to like force this into your head? Again, I don't need you to force into your head. Why? Because if you understand the idea of the half and half and half and half and half, this is half to the power of n. Okay, if I have gone through 3 half-lives, what has happened? Half to the power of 3, 1/8. It has decayed to 1/8 of its mass. Okay, the biggest trick to half-life is the word by versus to. Okay, so just be very aware of questions that will use this. Okay, idea to this is question will tell you, hey, it decays to this value. Okay, or it decays by this value. Just be very aware of the difference. You will have a chance to try this. Okay. So you can. Okay, some examples that I need you to bring into exam, right? Okay, because 1 to 2 marks, I feel they may throw in 1 to 2 marks to ask you for some users. X-ray imaging, okay, this is okay. Okay, I want you to write down some examples for gamma rays. Gamma rays, what can you do with them? Okay, gamma rays can do detection, tumors. It can also destroy brain tumors. Beta particles, to treat thyroid disorder. Alpha particles, smoke detector. So some users of it, based on past year, based on other topics, okay, because this topic is entirely new, right? Okay, so we can't say for sure, hey, past year, 10 years, GV, the trend is this. Okay, but in general, for application users, right, typically they throw in 1 to 2 marks, ask you to snip. That's more of what they're concerned about. Okay, so I'll be very happy with this orange color things that you bring into exam. Okay, lastly, hazards. Hazards. Okay, hazards of radioactivity, somatic versus genetic. This one technically, I would say is FYI. Okay, I don't need you to be crazy over this hazards portion. Okay, just know that we need to limit our exposure to radioactivity. Why so? Because the gamma rays can penetrate into the human body. Okay, so hazards, you can think of it as, oh, gamma rays can penetrate through human skin, leading to things like this. Okay, so the somatic and genetic damage, take it as an FYI. Okay, the super important one is this. So if you don't know how to write gamma, right, you can write it like an I like that. It's more, it's sort of like a grass like that. Okay. Nuclear fusion and nuclear fission, this is the one that the Oppenheimer guy did. Okay, when these things happen, it releases freaking a lot of energy. That's why the atomic bomb will explode. Okay, so it is like intentionally introduced for these radioactive substances so that you put inside and they are going to fuse together or they are going to fission, meaning they break apart. Okay, this one I cannot have you like link exo and endo to this too much. Okay, because if you do right, then you might think of it as, oh, because I know that endothermic needs to absorb energy. Okay, if you want to link this idea, you can think of it as because in nuclear fission, right, this is already very unstable. The nucleus is very unstable, hence not a lot of energy is needed to absorb to break it apart. It was already going to break apart. Okay, so don't think too much. Okay, but it's I think a bit natural for you to think of. So main idea behind this is both of this situation are going to release a lot of energy. Okay, but fusion is the case of combine. Fission is the case of splitting. Okay, but both of it will release a lot. Okay, for nuclear fission, there's something that I need you to know to link it to nuclear chain reactions. Nuclear fusion in the process, right? I'm putting things combining together. What happens in the process? I'm releasing neutrons. Okay, very good. Here, okay, I'm producing neutron. Wait, sorry. Inverted. Fission. We go into fission first. Okay, in fission, what happens is I'm producing these neutrons. Here, split the target nucleus into two smaller isotopes, three high-speed neutrons. Why these neutrons is important, right? Because this neutron is going to collide again. Ejected high-speed neutrons start other fission reactions. This chain reaction that you see here can sometimes be called nuclear chain reactions. Okay, so something getting broken down releases other particles. High-speed neutrons then go and collide and make everything excited again. Then the fission occurs again. If the process keeps repeating, that's why they call this a nuclear chain reaction. Okay, that's why the whole idea of this, right, is typically bombarded by high-speed particles. Okay, that's why the process can repeat. Okay, and that is nuclear fission. Fusion, okay, nothing much I need to highlight for fusion. Okay, really nothing much for fusion. A way for you to remember fusion and fission, right, is really like if you think of like food fusion, like Asian, American fusion. I need to combine two things together. Okay, that's why nuclear fusion is combining things together. Okay, but fusion requires extreme pressure and temperature. That's why the nuclear energy or the nuclear store in our model that we are learning about, it typically is produced from nuclear fission. Because nuclear fusion in the first place requires that to happen. But nuclear fission itself, with something already unstable, it was already going to break apart. So with the neutrons colliding, the process can keep repeating and generate high amounts of energy. Yeah, so the whole idea, the whole topic on the radioactivity links back to the nuclear store that we saw back in chapter 7, core energy power. Okay. Okay, so typically questions will test things like the half-life graph, which is known as the decay curve as well. Okay, sorry, forget to tell you all this. This time sometimes you will see decay curves, it's the same thing. For you to study what happens with the half-life. So questions can typically test in terms of this. Typically test in terms of when I pass through magnetic field, what happens to the deflection. Know the charges of them very well. You should be able to answer most questions. We will discuss more in the topical worksheet that I'll be passing to you. It's 9:36, I'm so sorry. Based on the charges of them, we should be able to tell how they will deflect. That's why the charges are so. Okay, sorry to hold you back. Let me pass through your radioactivity worksheet and good to go. Okay. So this radioactivity I feel is a bit iffy in the sense of we don't know what to expect. Okay, so the questions are actually extracted from Cambridge International because Cambridge International last year this was already introduced. Okay, so we try some of the questions that they had done from there. Then we go there. We do it. For Juby and Karen, I'll be sending you the soft copy. Okay, but Karen, I will be passing you the hard copy as well. For Juby, oh, you will only come next Wednesday, so I will see you. Okay, so I was saying this. So sorry. Okay, for Juby and Karen, yeah, no more questions. You are free to drop off already. Stop the recording for next year as well.